Hello, AP Stats. We are doing a video on Chapter 25, Paired Samples and Blocks, out of our textbook. So make sure you've got your book with you and your calculator. We're going to do a problem from the book and a writing utensil and paper. And we'll get right into it. One nice thing about Chapter 25 is this is the last chapter that will be covered in the AP test. So we're going to add one more interval and test to our confidence intervals and our hypothesis test. We have the 1 proportion Z interval and test, Z-score, normal model. 2 proportion Z interval and test. Those are the proportions ones. We have our 1 sample T interval and test, 2 sample T interval and test, T for the T model, dealing with means. So these are proportions, these are means, and Chapter 25 is another means interval and test. So we're still working with averages, with means, and we're still working with the T model. And let's just write those down right now on our list here. And the interval is going to be the paired T interval from Chapter 25, and then a paired T test from Chapter 25. The paired T interval and the paired T test. Chapter 25 is about the special situation, the matched pairs situation. And then what's the calculator command for these paired T interval and the paired T test from Chapter 25? And it's just actually T interval and T test. And you'll see why. So we're just using T interval and T test for our calculator commands, because we're actually only doing a 1 sample T interval and a 1 sample T test in Chapter 25. Okay? All right, so let's go to chapter number 19 on Chapter 25, and we're going to work through that one together. Number 19. Okay, now first up, matched pairs. What's a matched pairs situation? Let me give you one, and I'm just kind of thinking off the top of my head. All right, so let's say a non-matched pairs situation would be, we want to know if there's a difference between the average SAT score for a David Douglas student and an average SAT score for a Reynolds student. Okay, so what do? We take a random sample of 100 David Douglas students who took the SAT, a random sample of 100 Reynolds students who took the SAT, and then we average the David Douglas students, and we average the Reynolds students, and then we have the mean from our sample, we have the mean from our sample 100, and then we say, is one higher than the other? Did one school do better than the other? Is there a difference between the means? And then you find that sample difference, and then if you're doing a confidence interval, you reach out from that sample difference. If you're doing a hypothesis test, you have the null that there's no difference. The mean, the average SAT score for David Douglas equals the average score for Reynolds. And that's just a 2 sample T interval and test. 2 sample for means, Chapter 24, okay? Okay, what's different in Chapter 25? The matched pairs test, the matched pairs interval. And you guys might remember matched pairs. We talked about that in the experiment. It's like a special type of experiment, is a matched pairs. We gave one example with like the new type of socks you're wearing. Actually, I wasn't here. Was I here when you guys read this? I don't know. But let's say we have a new type of sock that doesn't get holes in it, apparently, and we're going to test it to see if it's better. And so we have 50 subjects. Now, instead of randomly assigning 25 to the new socks, 25 to the old socks, and then they all walk, recollect the socks, and then, grade their wear and tear somehow, okay? That's one way to do it. But here's a problem. What if you randomly had 50 people, 25 randomly got the old, 25 randomly gave the new? What if the 25 that got the new socks, who are supposedly better, what if they happened to have more people in that group who exercised more and walked more? And in the group of 25 that got the old sock, they just happened to be more people in that group who didn't exercise and stuff. So the new sock, which let's say it was actually better, okay, but everyone in that group was exercising all the time and stuff, right? Or just randomness. They just happened to exercise more. The old group, they didn't exercise more. And then when you looked at their wear tear, even though the new sock was actually better because they exercised, it had the same wear and tear as the old sock. The people didn't exercise. And then your results didn't look good in the end, right? So what's a better way to do it? Well, with those 50 people, have each individual person wear a new sock and an old sock on the same feet, a left foot and a right foot. Still do randomness. Randomly, like flip a coin and decide what foot, randomly assign treatment. So what foot got the standard? What foot got the new? And you randomly decide, assign the treatments. And then after a month, when you get all the pairs of socks back, you look at each pair of socks for each person and say, for this person, is there a difference? For this person, is there a difference? For this subject, is there a difference? And then you look at all those individual differences for all those 50 people, okay? And then you're gonna have a one sample group of all the differences for each subject. Each subject will have a difference, and that's a matched pairs. And that's better. If you can do a matched pairs, it's a better way to do it. It eliminates variability. There were other examples of matched pairs. You know, you could have like twins do a medical study because their genetics are similar. Or you can have, like with our David Douglas Reynolds example, you could have, what if you had like, oh, I don't know, this is totally not real, but what if you happen to have 20 families with one kid at David Douglas and one kid at Reynolds? That would never happen. But what if you did? And then you said, okay, well now let's compare the GPAs of those 20 families, those pairs of students, because then they would come from the same family, so they would have had the same parents and the same, help with their studies and same income level, and then you could just look at each individual pair. Which sibling did better, the David Douglas sibling or the Reynolds sibling? So when do you do matched pairs? If there's a natural pairing, when the subjects are paired up, to eliminate, variability in the data, you would have a matched pair situation. And so you want to look for that. Oh, it's a problem that deals with means. Great. Well, is that a one sample? Is that a two sample? Or is it a matched pairs situation? Is what you're going to ask yourself now. And the AP test does like matched pairs. They often use matched pairs stuff. I don't know about this year, but in the past they have. Okay, so let's do it. Let's do a matched pairs problem. So we're on number 19 on page 605 in the book. Job satisfaction, chapter 25, number 19. I'll read it. A company institutes an exercise break for its workers to see if it will improve job satisfaction. Take a break, exercise. And will that improve workers' job satisfaction? Scores for 10 randomly selected workers, okay, so 10 randomly selected workers before and after the implementation of the exercise program are shown in the table below. Okay, so what was your job satisfaction before? Now do this program and exercise and take breaks. Now what's your job satisfaction after? Okay. Okay, A, identify the procedure you would use to assess the effectiveness of the exercise program and check to see if the conditions, okay. 2, test an appropriate hypothesis, state your conclusion. And then 3, C, ABC, C, if your conclusion turns out to be incorrect, what type of error did you commit? Ooh, we can do a type 1, type 2 error piece too. Okay, so let's just do the test. What do you need? Let's pretend like we're taking the AP test. Let's do the test. Is there evidence to see the effectiveness of the program? And so when it says the effectiveness of the program, I want to say, is there evidence that it worked? Is the program effective? Has job satisfaction increased after they've done the program? Okay, now here's your first clue to know this is a matched pairs problem. See how it says worker 1, a before and after, worker 2, a before and after, worker 3, a before and after. Each subject has 2 pieces of data that goes with it. Whenever you have 2 pieces of data that are linked, either they came from the same subject or the two subjects that they came from are linked somehow, like a twin or brother and sister or something like that, that's your clue. Oh, this is a matched pairs. So we're going to do a paired t-test. Paired t-test. Name it. Paired t-test. Okay. Okay, so now let's write our hypotheses. What's the null? What's the alternative? And there's a special way to write these. So you want to know how to write these. Now, the null is that there's no difference, right? The before, the after satisfaction level is the same. No difference. It's just like chapter 22, just like chapter 24, just like all the two sample stuff. The null is that there's no difference. Here's how we write it. We say the mean of the differences equals 0. That's how you write it. Well, first, let me explain what we're going to do. Before we even get to that, let's explain what we're going to do, okay? First, let's put all of this data into our calculator, all right? So I got my stat enter, okay, my list 1, list 2. I'm going to put before and after. I'm guessing the after will be higher than the before, but I guess it doesn't really matter how we enter that in. So I'll just enter it in as the book puts it, okay? So the book puts before in the first column, after in the second. So I'll put before in list 1, after in list 2, and make sure they line up. All right, now one way to do this is to just average all the before people in that sample. What's that sample of 10? Or what's that average from that sample of 10? Average the after people, or average the after scores. Okay, and then compare the means of the before and compare with the mean of the after. That's a 2 sample. We're not doing that. That's chapter 24, right? 2 samples, compare their means. No, what are we doing? Well, it's not just one big sample and one big sample. In both samples, they're paired together, right? So what we're going to do is we're going to find the difference between each pair. What's the difference between the before and the after for worker 1? What's the difference between the before and the after for person 2? What's the difference between the before and the after for person 3? And if you find that these differences are negative, or if the differences are mostly positive, well, then that's going to tell you something about the program, right? So we need to find the differences between each pair. And that's what we're going to do our 1 sample interval, or our 1 sample test on the differences between each pair. And here's how you can find those differences really easy on the calculator. So I'm gonna figure out what's the difference between 26 and 37, 27 and 41, 24 and 39. Here's how you can get those differences really easily. We'll throw them in list 3. So highlight list 3, hit enter. Bam, enter on list 3, there we are. And I want all of these differences. Here's how you can get them. You could type in right there, list 1 minus list 2. So second 1, L1, minus second 2, L2. See, I just typed in list 1 minus list 2, and look what it does. There, it throws all the differences in for me between each pair. There are my differences. So list 3 is what we're using. Those are all the differences, and they look negative. Mostly, not all. But that means that the before was smaller than the after. So it looks like the program helped, right? But is that just due to sampling variability, or did it actually help? Okay. Okay, so what is this? Hold on, find my pen. There we go. So what is this mean little d in my null? Mean little d equals 0. That's the mean of the differences. So I'm going to define that. That is the mean of the differences. And then I'm going to put before minus after. I normally like to keep those positive. I didn't do that here this time. It doesn't really matter though. So the mean of the differences, and I'm going to put before minus after in parentheses for each worker. The mean of the differences before minus after. I'll put a little more context. The mean of the differences of the satisfaction level of the job satisfaction satisfaction level for each worker. Okay, that's how I define that. What is this thing? What is that mean of the little d? Then that's the mean of the differences. And I did before minus after of the job satisfaction level, mean of the differences of the job satisfaction level for each worker. That's what that is. That's my list 3. It's all the differences, all the differences. And we want to see if we look at all those differences and if you average them, we want to see if it is less than 0, right? We want to see if the program is effective. And if it's effective, then the before minus after will be negative, because the before you would give a low job satisfaction level. But then you did the exercises. And then the after, you have a higher one because you enjoyed it. It was effective. And so you have a smaller minus a higher number would give you a negative average. And it did look like we had a lot of negatives in there. So those are the hypotheses. Okay, it's always going to be the mean of the differences equals 0 for your null every time for matched pairs. And then this could be a greater than or a less than or a not equal to for a two-tailed there. Okay. Okay, let's check the conditions now. Okay, was this a random sample? And it did say 10 randomly selected workers. Okay, that's good. It doesn't say 10 volunteers, right? It says 10 randomly selected workers. We like that. So random, let's give it a check and say the workers were randomly selected. This is an experiment situation, not a sampling. So it's good to remember the workers were randomly selected. I am writing these down this time. Okay, 10%. Now 10% doesn't apply. So I'm just going to put a, doesn't apply in an experiment situation. Doesn't apply in an experiment situation. We're okay, good. 3. Okay, yep. Okay, the sample size condition. And remember, we're talking means, right? We're in means. Chapter 23, 24, 25 all go together. It's still all means. It's all the T model. So large enough sample. Large enough sample. Okay, now here's a little tricky. Do we have to show histograms for both samples? We have 3 samples. I have the before, I have the after, and I have the differences. Well, we're just doing a 1 sample on the differences. So the only thing we care about are the differences here. Okay, so 1 histogram. Now, do we have greater than 30? No, we only have 10. So it should be unimodal symmetric. These differences should be unimodal symmetric for the large enough sample condition to be satisfied. So what do we have to do? We have to make a histogram of list 3, a histogram of the differences. So second stat plot, second y equals, turn your stat plot on, histogram list 3. Now, list 3, that's where all the differences are scored or are stored, okay? And let's do zoom stat on that, zoom 9. That looks pretty good. I'm gonna kind of tinker with it and then make nice whole number bins. So I go to window, there's my window, a lot of decimals. So my min is -21 to my max 10.25. I'm gonna say, how about -25 to 15. And my scale, I'll make 5 for my X scale. And I'll make my Y max go up to 6 just in case it gets high. Okay, so that's what I've got. Now, it might not look good. We might have to mess with that. I went from -25 to 15, 5 in each bin. Unimodal symmetric. Let me see if I could do something with that. Let's make 10 in each bin. No, I don't like that. Hold on, let me tinker with this a little bit, which is totally fine. You're allowed to do this. That's pretty good. Well, here. Negative. And you probably want to spend too much time on that. That's pretty good. That's pretty unimodal symmetric-ish, right? It goes, it's pretty good. I'm gonna use that, okay? All right, so then you quick sketch that out. I know, bear with me, people. All right, well, I won't waste you guys' time, but sketch out the histogram, okay? So here's what I'm gonna say. The sample is small, and then I'm gonna put n is less than 30 in parentheses, but it is unimodal and symmetric enough to proceed, is what I'm going to say there. Okay, so yes, do a better sketch of that histogram. I'm just put a scale on it. Okay, I just don't want to make this video go on forever. But here's what I said: large enough sample condition. The sample is small and is less than 30, but it is unimodal and symmetric enough to proceed. What I would also do is label that. I would say the sample of the differences. The sample of the differences. Tell them what you're looking at. It's the differences. It's the differences between each pair. It's the before minus the after. The sample of the differences is small, less than 30, but it is unimodal and symmetric enough to proceed. Check. Okay, number 4, the last condition, the new condition. So we have random, 10%, large enough sample. The last condition is just to make sure that you can actually do a paired t-test. Is the data matched pairs? Is the data paired? And it's called the paired data condition. And it's a really easy one. Is this data paired? And I will say this. I'll say each worker has a before and after score. So the data is paired. Something like that. Each worker has a before and after score, job satisfaction score. So the data is paired. Check. All conditions met. Each worker has a before and after score, so the data is paired. You could say, yeah, just talk about how the data is paired, and you're good to go. Okay. Okay, so let's do the test. Let's do the test. What are we going to do? We are going to do, how do you do a paired t-test? You just do a regular t-test, a one sample t-test, a one sample t-test on what? On the differences between each pair. So a regular t-test from list 3. We have the data. We do have the data. We have the data, and it's all in list 3. What's the null? Well, the null is 0. The null is that there's no difference. Data's in list 3, and I want less than. I want less than for my alternative. So there's everything. Data in a list. The null is no difference. All my differences are in list 3. Always keep that 1, a less than, and calculate. Boom. What do we give them? We give them the t-score, the test statistic, the p-value, and what else? The degrees of freedom. Got to give them the degrees of freedom. They don't give it to you on your calculator here, so we got to remember to write that down. Okay, my t-score is negative 3.597. My p-value is 0.00289. What's the degrees of freedom for a one sample t-test? One sample, n minus 1. So in this case, it's going to be 10 minus 1. 9 degrees of freedom. They do need that, and it doesn't give it to you on your calculator. You gotta give degrees of freedom is 9. So there's the test statistic, there's the p-value. Pretty low. So name it. Write your hypotheses. The mean of the differences equals 0, and then it's always going to be the mean of the differences. Is how you write a paired t-test hypotheses. Define that mean of the differences. Check your conditions. Paired data condition. The data are naturally paired. Each subject has a before and after score. It's naturally paired. Okay. Do a histogram of the differences. When? if there are less than 30 differences, right? Less than 30, got to have a histogram, a nicer one than that. All right, then just do one sample t-test on the calculator on list 3. Bam, let's state our conclusion. With a p-value, so what? I'm going to say using alpha equals 0.05 with a p-value so low, we reject the null. There is sufficient evidence of what? Let me look at the problem. Number 19 says, assess the effectiveness of the exercise program. So you know what? We could even say, if you want to be really, you could just say it like this. There is sufficient evidence that the mean of the differences before minus after of the job satisfaction level for each worker is less than 0. Okay, you could just repeat it just like that, alternative hypothesis in context. Or if you want to use the language of the book, you could say there is sufficient evidence that the exercise program is effective in improving job satisfaction. There is sufficient evidence that the exercise program is effective in improving job satisfaction. I'll read that again. Using alpha equals 0.05, with the p-value so low, we reject the null. There is sufficient evidence that the exercise program is effective in improving job satisfaction. Done. That is a t-test. All right. Interpret the p-value. Well, if the mean of the differences before minus after of job satisfaction level for each worker is equal to 0, then there is a 0.00289 probability that we would have got an average of the differences in our sample or less due to sampling variability. Okay. This question also asks, type 1 or type 2 error could have been made. Well, what do we conclude? We went with the alternative. We concluded that it worked, right? We rejected the null. We concluded it worked. We made an error. We concluded this. What was the error? Well, we should have concluded that. So the error is that this is not true. The null is true. So what's that? The null is true. Type 1 error could have been made. The null was true, but we went with the alternative. Type 1 error, okay? What about a confidence interval? Well, let's name it quick. Let's do a quick 95% confidence interval. Everything's all in our calculator. Let's do a paired t interval. Name it, paired t interval. Check the conditions. Was it a random sample? Yes, the workers were randomly selected. 10%. Well, with these 10, less than 10% of all workers, well, it's kind of an experiment situation too. So, whatever you want to do there is they wouldn't ding you if you said these 10 workers are less than 10% of all workers. They wouldn't ding you for that. But you could also say this is an experiment, so 10% doesn't apply. I think that's fine too. Okay, large enough sample. We looked at it, check. It was unimodal, symmetric enough to proceed. Paired data. The data is naturally paired. Each worker has a before and after piece, so it's paired together. Okay, good. Name it, check the conditions, do it on your calculator. So we're going to go to t interval now. We're doing a one sample t interval, a chapter 23, one sample t interval, but we're doing it on the differences, which are in list 3. Okay, and I'm going to do a 95% confidence interval. A 95% confidence interval, how about? And there's your interval. So negative 13.85 to negative 3.155. And along with your interval, don't forget to put df equals 9. That is necessary. You are using the T model with 9 degrees of freedom. 9 degrees of freedom there. Don't forget that. Okay. And then you would say, we are 95% confident that the true mean of the differences before minus after of job satisfaction level for each worker is between negative 13.85 to negative 3.155. You could also say we are 95% confident that after completing the exercise program, the workers would score their job satisfaction between 3.155 and 13.85 more. Or we're 95% confident that after the exercise program, the workers would have improved their job satisfaction score between 3.155 and 13.85 points, is how you could say that. Okay. All right, there you go. Thanks, guys. That is chapter 25. I'll get working on the homework and stuff, but thank you for watching. Appreciate that.